Good day, everyone. Today we're going to be looking at how light is able to refract as it moves through its different mediums. By the end of this lesson, the goal is that you should be able to predict what direction light is going to refract in and apply a couple of kind of small physics laws so that you can accurately get ready for ray diagrams. So let's go ahead and kind of get started. I'll skip that. Let's start with just a quick recap of different parts of kind of the reflection diagram that you were given earlier. So you should be able to identify the angle of incidence, the angle of reflection, the normal ray, incident rays, and reflected rays when given a diagram that looks like this. And so with this diagram, the first thing I want to identify is that we have two arrows. This one over here on the left is heading towards the mirror. This one on the right is heading away from the mirror. So the one away from the mirror has been reflected. So that's our reflected ray. And the one that's going towards the mirror is what we're going to refer to as our incident ray. I like to say it is incoming, therefore it is incident. Our little dotted line right here is going to be our normal line. That's going to be important to know, especially as we get into drawing diagrams today. You'll see that the normal line becomes kind of a key element here. And then the last one is that we have our two angles. We have the angle of incidence and we have the angle of reflection. And the important thing to remember for those is that those angles are always measured from the normal line to the ray. And so that's going to be these kind of colored in shaded sections that I'm making right here. Our angle of incidence is on the side with the incident ray, so it's going to be this one right here, and our angle of reflection will be over here on the side with the reflected ray. So this will be my angle of incidence, I, and this will be my angle of reflection, R. So those are going to be the 5 parts of the reflection diagram that you should be able to tell me. Let's just kind of recap what it means for refraction to happen. When waves go through something, their medium that they're working through, if that medium changes, it also changes the speed that the wave is going at. Since we have established that light waves are in fact waves, that means light waves can also go through refraction. And so if I change the medium that the light wave is traveling through, that will cause the light wave to bend in a predictable way. And so that's this idea of reflection. Now, how exactly does light refract? So we know that light is moving extremely fast. We talk about things moving at the speed of light in science. It's the fastest thing that we can come up with. But even though it is moving extremely fast, we can get it to slow down a little bit by changing what medium it is going through. So we can get its speed to change. And because of this change in speed, its angle is going to change a little bit. And that's going to lead to some interesting kind of optical illusions and things. So it might appear to warp the material that it's going through. Hot air, water, things like that will cause kind of some interesting optical illusions to happen. But how much that the light bends is going to depend on how quickly the light is moving as it enters and how quickly the light is moving as it leaves. Or if I wanted to say that in a little bit more concise way, how much the speed of light is going to change as it moves from one medium to the next. And so one example of this is what we call the least time principle. Let's say over here on the left, we've got a lifeguard who's hanging out the lifeguard station, and they see somebody drowning in the water. Now, if the lifeguard wants to save the drowning person in as effective way as possible, it turns out in this situation, trying to go straight, like all the way this way from the lifeguard station to the drowning person, not the fastest route, because swimming takes longer, or it's slower. Swimming requires more effort. It takes the person longer to swim a distance than it would to run it. And so the fastest way for our person to actually go is to spend more time running, even if the total distance increases. They spend more time running on the sand than they do swimming in the water. That's our fastest route, and you can see that one kind of represented with the dotted line here. So that is the easiest way for the lifeguard to get to the person in the least amount of time. And so we call this the least time principle. And light does the same thing. Light is going to bend a little bit based on the fastest route from point A to point B. And so we get these kind of important rules then. basically what you are going to need to know for drawing diagrams is that as light enters a prism, it's going to slow down and it bends towards the normal line. So as it's going into the prism, it bends towards the line, and as it leaves the prism, it's going to bend away from the normal line. And if I wanted to represent this on the image that I've got right here on the slide, let me kind of show you. So if I have, let's say this is my incident angle right here, and this is going to be my outgoing angle. Wherever our laser runs into the prism, the first thing I'm going to do is I'm going to draw in that normal line. So it looks kind of like that. And then I can do one on the other side as well. And again, I'm using a dotted line to represent the normal line, and it's at a 90-degree angle to the surface of the glass. And so you can see that I've formed 90-degree angles here to the prism. So if my prism surface looks like this is about a 90-degree angle. Now normally, I would expect my laser to continue going off in this direction as if it was going straight. But because we are entering a prism, we're going to change direction. And according to our rule, as it enters the prism, it's going to bend towards the normal line. So I'm going to take this line and I am going to shift it a little bit more towards my normal line. So I'm going to make it go this direction. And so the new direction for my laser is this way. I have made it go closer to the normal line. Now, as it leaves the prism, I'm going to do the opposite, and we're going to bend it away from the normal line. And so instead of doing this path, which is what I would have expected, it's now going to go over here. And so that's a basic prism diagram, and you will be responsible for being able to do a basic prism diagram as we get a little bit further into this week. You're going to have a couple of examples where that has to be a thing. And as kind of an example of what this might look like in real life, if you've ever tried to swim for something at the bottom of a pool, you might be able to see it, you know where it's at, and then you dive down into the water and you realize that you missed the target completely. That's because light is bending as it's entering and leaving the water, and it's giving you an optical illusion. So if you take a look at this gentleman over here on the left in the pool of water, he hasn't lost his head or relocated it to the left. It's just that light is bending as it's going through the water, and so it's kind of shifting where we're expecting to see things. Same thing with this straw over here in this glass of water. It's a single straw, but because of how light is bending and slowing down as it moves through the water versus the air, we get these kind of interesting optical illusions. So that gives you kind of an idea of what refraction is going to look like in real life. Now I've got an example problem right here looking at 3 different arrows. There's green, blue, and orange, and the question asks which color arrow represents the correct direction for the light to go. So we have light that is entering a prism. So here's our light ray, is entering the prism. And our rule stated earlier that when light enters the prism, it is going to bend towards our normal line. The normal line is already represented here with the dashed red line. If the light was to continue going straight, it would have been blue, and we know that it is going to go towards the normal line. So we're going to shift our light ray this way, and we should wind up with the green arrow being the arrow that has the correct direction for light entering the prism. So just kind of a quick little check for understanding there. The final topic that we look at then for refraction of light is the role of triangular prisms and breaking up light into its component colors. So most of us are already familiar with the idea that white light contains all of the different colors of the rainbow, and that we can use things like prisms to break those colors up so that we can actually see them. Most of us at some point have seen a rainbow. We've seen light moving through glass and it changes, or it shows all of its colors. And so that's refraction happening through basically a prism that is not simply a square or a rectangle. So triangular prisms are the ones that we found break up light the most effectively. And so what you have is that all these different colors of the rainbow, and you've got your 7 colors, violet, indigo, blue, green, yellow, orange, and red. All of those colors are just slightly different wavelengths of light. So they all move at the same speed, but they all have different frequencies. And so as you kind of stretch them out, you get at the kind of the low end here, the smallest wavelength is going to be violet, and you can see that in the lower right corner, moving all the way down to red, which has the largest wavelength. So the only difference in the color that we see is going to be the wavelength of light. Now, what we found is that long wavelengths refract less than our shorter wavelengths do. So as they're moving through the prism, the red wavelengths basically keep going as straight as possible. Well, violet tends to refract the most, and over a distance as it moves across that prism, you get kind of the colors begin to break up. And so triangular prisms will do this, and you'll always wind up with this pattern where you get your red up top and you get your violet down below. And that's just how they break up all of those colors. And so that's essentially the end of refraction. I know there's a couple of additional slides on there for EM waves, and I'm just going to go ahead and skip those, which means you don't have to do this final question here for the summary section. But go ahead and going back through your notes, see if you can find what it means for something to be refracting. What's our basic rule for as light goes, how light interacts with the normal line as it leaves a glass prism, and then what happens as white light breaks apart in a triangular prism. You should be able to answer those 3 questions by the end of this lesson. And I'll see you in class.